Hi, my name is Tony. I'm a staff member here at the newer campus of COTC, and Emily's asked me to once in a while give you maybe tips from my experience with tutoring calculus over many years. And so this will be my first lesson. I want to introduce myself. We have a lot of hours here on this campus, but we also have some tutoring at the other campuses. Now, the first lesson is called L'Hopital's rule, and that handout she has does a really good job of explaining the rule and many examples of it. So I'll just give a couple of insights that might tell you how to think in a mathematical way. So let me start off with a really easy example, okay? So suppose I asked you the limit x goes to infinity of 6x plus 8, 3x minus 1. So this is even covered in algebra classes as a horizontal asymptote. So notice that they have the same degree of 1, and so when they're the same degree, the limit is simply the leading coefficients. So the answer is 6 over 3, which is just 2. So it's a pretty simple example. But notice something very interesting about this example. The 6 and the 3 happen to also be the derivatives of the top and bottom. And so it turns out that that rule applies in general. And so that's what L'Hopital's rule is about. Now, by no means is this, of course, a proof, but it's just an intuitive way to see why sometimes when people do mathematics, they notice a pattern and then they say, hey, maybe this pattern keeps happening. And if the pattern does keep happening, they're like, wow, this is pretty amazing. Another example would be, for example, limit x goes to infinity of something like x squared plus 8 over x minus 1. So again, the numerator has a higher degree, so you probably know that the limit is infinity. But again, if you notice the derivatives, you would have 2x over 1, which is just 2x, which also goes to infinity. So again, that's not a proof, but that's an interesting way to see why L'Hopital's rule works. Now, another thing, as is mentioned in the handout, another thing to realize is L'Hopital's rule is not related to what's called the quotient rule. So for example, when we do a derivative, if I do the derivative of this function, that's a separate issue from L'Hopital's rule. And so, again, it's explained in the handout pretty fine. But let me also mention that sometimes in math things look alike, but they're actually different. Another common example is the difference between derivatives and the logarithm. So for example, if I say, what's the derivative of x squared, the 2 comes down. And if I say, what is log of x squared, the 2 comes down. But notice they have nothing to do with each other. It's just a coincidence, actually. So just realize L'Hopital's rule really has nothing to do with the quotient rule. They're two different rules. Lastly, I want to mention, hi. Okay, so the last example I want to talk about deals with what's called a hierarchy of functions. It refers to how fast a function grows, which will play really important roles later in this course. Okay, so when you have powers of x, it's pretty obvious that the higher the power of x, the faster the function grows. Okay, technically for x bigger than 1, but we are referring to going to infinity. Now, smaller than x would be a constant, and the simplest constant is the number 1. Now, the reason I left a gap there is because between, there's a function that actually goes to infinity, but yet slower than any power of x, and that's the logarithm function. Okay, and in that handout, they give an example of, they show why log grows slower, and you use L'Hopital's rule to show that. Now, your intuition might then tell you that if log grows slower than any power of x, which are polynomials, then the inverse of log would make sense to grow faster, and sure enough it does. And as you hopefully know, the inverse of the logarithm is an exponential function. The most basic one is e to the x. But that's not a proof. So I can prove to you that e to the x grows faster than any power of x. Now, the proof should show any power, but I'll stick to something simple like the second power. I don't want to be too abstract. So how will I show that? So what I do is I'll show the limit as x goes to infinity of e to the x over x squared. So again, if you just plug in the infinity, you'll get the indeterminate form of infinity over infinity, and that's exactly when you use L'Hopital's rule. So applying L'Hopital's rule, you take the derivatives, and so notice that e to the x stays the same, and x squared knocks down a power. Well, again, they both go to infinity. So we use L'Hopital again. And notice now we have e to the x over 2. And that does go to infinity, because e to the x goes to infinity, and dividing by 2 doesn't change that. And so that actually proves that e to the x grows faster than any power of x. And so again, that's a very interesting application, which shows the relative growth of functions, which will play a really important part later in this course. And thank you for paying attention.